Hi, welcome to chapter 15, Benzene and Aromaticity. My name is Ramon Rios and I will give you this lecture. Okay, remember that this video recording is not made to substitute the in-live lectures. It's in order to help and reinforce your study. What we will explain today will be basically the sources and names of aromatic compounds, structure and stability of benzene. We will talk about the aromaticity and the Huckel 4n+2 rule, aromatic ions, and finally we will talk about aromatic heterocycles. We will focus in pyridine, and pyrrole. Okay? Well, when we talk about aromaticity, about aromatic compounds, it refers to a class of compounds that contain normally six-membered benzene-like rings with free double bonds in alternate positions. Here you can see the benzene. Okay. Here the benzene. Here the benzene. Here we have benzaldehyde, or here toluene. All the rings, as you can see, are six-member rings with conjugated double bonds in alternative positions, single double bond. Okay. Another characteristic of these rings is that all the atoms, as you can see, are sp2 hybridized. Okay. These aromatic rings are present in the major part of aromatics of natural products and pharmaceuticals. As you can see here, I put some examples of scrone and a 4-acetylene that contains aromatic rings in his structure. Okay. Here you can see that one of the most important aspects of benzene is that a lot of benzene rings with different substituents has his own name. That means, for example, we have benzene and we have the methylbenzene, but instead of methylbenzene, normally the people call this compound toluene, as you can see here. If we have two methyls, it's called xylene or xylane. If we have a fused 5-member ring, also with a double bond, it's called indene. If we have two aromatic rings fused by one side, by one bond, basically it's called naphthalene. If are joined by only one bond, carbon-carbon bond, is called binaphthyl. If we have free fused benzenes but in a linear way, it's called anthracene. And finally, if it's in an angular way, it's called phenanthrene. I am sorry, but you need to know these names. You need to memorize all these names. Okay. Also, some monosubstituted benzenes are named by his own name. For example, okay, we have the aminobenzene is called aniline. The benzene carbaldehyde is called benzaldehyde. The acid is called benzoic acid, etc., etc., etc. The double bond is called estidene. That means you need to remember and you need to memorize these names because it's the names that we will use when we write the name of different aromatic compounds. Okay? If you are lucky and the compound that we are not naming, doesn't have his own name, what we will do is exactly the same that we do when we do the nomenclature of alkanes. Okay, for example, here we have a benzene that has a bromo, will be bromobenzene. You can ask me why it's not one bromobenzene, but when we have a cycle, always, if we only have one substituent, this substituent will be in position 1. That means it's redundant that we say one bromobenzene. I will not say that it's totally incorrect, but give us the same information than bromobenzene. If we have a nitro, is exactly the same. We have nitrobenzene. If we have alkyl chain, for example, we can have a propylbenzene. Interestingly, when we have alkyl chains, we can decide, or we can choose between to put as a main chain the acyclic chain or the aromatic ring. For example, here you can see in this compound how we use the benzene ring as substituent. And one thing that we have to be careful is that when we are using the benzene ring as substituent, the name is phenyl. Okay, remember that in the case of alkane, for example, methane, if it's as a substituent, will be methyl. We change the N for -il. In the case of benzene, we change totally. It's not benzene, benzyl, it's benzene, phenyl. Okay, why? Because phenyl is basically when we have a benzene ring followed with a CH2. Then it's benzyl. Okay, again, don't ask me why. It's what it is. You need to memorize this. Okay, these substituted benzenes are named by the number. We can do the numeration. For example, here we have benzene that is substituted dichloro, and we start counting with 1 chloro, and it's 1,2-dichlorobenzene. But also, if we want to use an old nomenclature, we can change the 1,2-dichloro for ortho. Ortho means that we have two substituents in 1,2 position. Okay, that means that this will be ortho-dichlorobenzene or 1,2-dichlorobenzene. Both are correct. If instead of 1,2 we have 1,3, as you can see in the next example, okay, this compound is called meta-dimethylbenzene or 1,3-dimethylbenzene. Okay, and if you remember, when we have a benzene substituted with 2 methyls, also is a meta-xylene. Okay, you can use all these names. In the last example, what we have is a substituted benzene with aldehyde and with chloride. Okay, how we name this compound? This will be, we know that a benzene plus an aldehyde is benzaldehyde. That means that we only need to substitute, to put the substitution of the chloride, and could be 4-chlorobenzaldehyde, okay, or para-chlorobenzaldehyde. Both names are correct. Okay, that means that, remember, when we have a desubstituted and only work with desubstituted benzenes, okay, if we have a 1,2 disposition will be ortho, 1,3 disposition will be meta, 1,4 disposition will be para. If we have more than 2 substituents, what we need to do is to numerate, okay, putting the carbon number 1 in the carbon that gives us the lower numeration for the substituents. Okay? For example, if we have this, if we put 1 here, we have 1, 2, 3, 4. That means that this will be 1, 2, 4. If we do the opposite, 1, 2, 3, 4, 5. 1, 2, 5. Obviously, it will be better 1 to 4 than not 1 to 5. That means that the number 1 will be this one, and we will go in this direction. That means that this will be a 4-bromo, bromo is in position 4, 1,2-dimethylbenzene. The next one we do exactly the same. In this case, in order to get the lower numeration, we need to put the 1 in the wedge and then go into the methyl as number 2, and then the other methyl is number 5. If we do anything else, will give us higher numbers. Okay? And in the case of nitrotoluene, what we do is, we know that this compound, when we have a metal, is toluene, and then the only that we need is to name the where are the nicros. In this case, will be 2, 4, 6 3-nitrotoluene. Okay, why? Because if we say toluene must be in the position 1. Okay, in the same case before, because we say phenyl, because we know that a benzene ring with an alcohol is a phenyl. If we say phenyl, the alcohol must be in position 1. That means will be a 2,5-dimethyl phenyl. Okay? When we have, in summary, when we have more than 2 substituents, we have to check which is the lower numeration. If we are using a name of a compound, for example, phenyl or toluene, the K characteristic of phenyl, in this case the OH, or the K characteristic of toluene, that will be the methyl, will be the number 1. And then we have to find the lower numeration possible for the rest of the substituents, taking the methyl or the hydroxyl, depending on which we are using, as a number 1. Okay, problem 15.2. Give the UPAC name for the following compounds. Well, the first is bromochloro, that I will put that is meta-bromochlorobenzene. Okay? Why I put bromo before chloro? Because remember, all the substituents always are by alphabetical order. In the case of B, we have 1, 2, 3, 4. I am checking the longer alkyl chain, and then I start numerating by the carbon that is attached to the phenyl, because if I do this, the substituents are in 1, 3. If I do the opposite, the substituents will be in 2, 4. That means I will choose this and will be 3 methyl, 1 phenyl, butane. Okay? Remember, why methyl? Because M is before P in the alphabet. Okay? And why phenyl? Because remember that when a benzene is not the main group, it's called phenyl, not benzyl. This is a very, very common mistake in the first years. Please don't do it. C, this is, we remember that a benzene ring with a NH2 is called aniline, and then will be para-bromoaniline or 4-bromoaniline. The next one, D, we know that it's toluene. If it is toluene, then we put the 1 in the methyl. If we say toluene, 2, 3, 4, 5. Okay? It's the lower possible numeration, 1 to 5. That means that will be 2,5-dichlorotoluene. Next one, we don't have any name. That means that this will be free. We put the 1 in the ethyl, 2 in the nitro, and then it's 1, 2, 4. There are no any other numeration that is lower. That means that this will be 1 ethyl, 2, 4-dinitro benzene. And finally, the last one will be 1, 2, 3, 4, 5. There are no any possible lower numeration. Okay, will be 1, 2, 3, 5 tetramethyl benzene. Okay? Good. Then, one of the characteristics of benzene is that a lot of people was thinking that a benzene, because it's a cyclic ring with 3 double bonds, his reactivity will be quite similar to the reactivity of a double bond. However, this is totally false. Okay? If we have a double bond, remember that if we have a double bond and we create with bromine, what we expect is that we form the intermediate of the bromonium ion, and later on we get the dibromination. Yeah? However, when we do a bromination in the case of benzene, what we get is nothing. There are no reaction. First surprise. In order to get a reaction, we have to force the condition. We have to add a catalyst that will be iron cribromide. This iron cribromide is able to activate the bromine, and then we have a monobromination instead of the expected dibromination. That means the chemistry of benzene is very different to the chemistry of a double bond. Okay? Another experiment that has been done is how much is the hydrogenation of the double bonds of a benzene. Okay, that means if we have a cyclohexane, as you can see here, basically we want to hydrogenate a cyclohexane, what we get is 118 kilojoules. If we hydrogenate 2 double bonds, that means the one free cyclohexadiene, what we get is 230 kilojoules. That means until here everything is normal. If for 1 we get 118, for 2 we will get more or less the double. It's not the double because it's not twice the same molecule, but has to be quite similar. However, when we hydrogenate the benzene, instead to get 300 something, what we get is 206. That means we get less energy than when we hydrogenate a cyclohexadiene. Why? Because the benzene ring has an extra stability. Okay, because it's aromatic and has a lot of resonance forms, has an extra stability, and this extra stability in this case is 160 kilojoules. That means this makes that the hydrogenation of the double bond is less energetic than, for example, the hydrogenation of 2 simple double bonds. Okay? That makes these compounds by far more stable than not double bonds. And their reactivity will be by far lower. This concept of aromaticity, we can extend it to other compounds, other cyclic compounds. Okay? And basically, Huckel was studying this type of compounds and arrived to the conclusion that a molecule is aromatic only if it's planar. All the atoms of the ring must be at least sp2 hybridization, sp2 or sp. Okay, that means that they have to get a pz orbital in order to form the p system. And the number of electrons in this p system, the number of electrons in orbitals p, must be 4n plus 2, following the series 4n plus 2. That means where n is a natural number means or 2 electrons, or 6 electrons, or 10 electrons, or 14 electrons. Okay? Following these rules, we can check these 2 compounds that looks like aromatic, cyclobutadiene and cyclooctatetraene. In the case of cyclobutadiene, as you can see here, well, we have a 4-member ring with 2 double bonds. Okay? This is planar. All the atoms are sp2. What is the problem? That if we count the electrons, we only have 2 of this double bond and 2 of this double bond. That means 4 electrons. 4 electrons is not following the 4n plus 2 rule. 4 electrons is following the 4n rule. And when some compound that looks aromatic follows the 4n rule, we say that it's anti-aromatic and it's very unstable. It's just the opposite. Okay, aromatics are very stable, anti-aromatics are very unstable. In the case of cyclooctatetraene, it's happening the same. Again, all the carbons are sp2, looks like planar, but if we count the electrons, we have 2 of this double bond, 2 of this double bond, 2 of this double bond, and 2 of this double bond, total 8 electrons. 8 electrons is again following the 4n rule. That means that it's anti-aromatic, means very unstable. This type of compound will be very, very unstable. The same idea of aromaticity can be used in aromatic ions. Okay, here we can see aromatic ions, and we can see this example of cyclopentadienyl anion. Okay, the cyclopentadienyl anion is basically a 5-member ring with 2 double bonds where we remove 1 proton and we have a pair of electrons in one of the carbons. Remember that we have when we have an orbital with 1 electron or with 0 electrons or with 2 electrons, normally we can choose in which, if this orbital is in sp3 or is sp2 hybridized carbon, will be the pair of electrons or the electron or the 0 electron will be in the pz orbital. Okay, we can choose. We know that if we have a carbocation, we always choose the hybridization of the carbon as sp2, and we will have the lack of electrons, or the positive charge, on the pz orbital. We will have a pz orbital empty. However, when we have 2 electrons, the most stable thing that we can do is to put the 2 electrons in the sp3 orbital, in a hybridized sp3 orbital. Okay? However, if we put these 2 electrons in a sp2 hybridization in a pz orbital, and these 2 electrons make that the ring becomes aromatic, the stability gained by the aromaticity overcome the energy that we need to put the electrons in the pz orbital. That means, in the case of cyclopentenyl anion, okay, we have the pair of electrons in the pz orbital. Why? Because if we count, all the carbons are sp2 if we put the pair of electrons in the pz orbital, and then we have 2 electrons of this double bond, 2 electrons of this double bond, plus the 2 electrons of the negative charge, the 2 electrons that are in the pz orbital. We have 6 electrons. Will be aromatic. Okay? What happens in the cycloheptacryanyl cation? Well, again, if we have a carbocation, this time is easy. We have by sure a hybridization sp2 in this carbon. That means all the carbons of the ring are sp2, and we check the number of electrons. We have 2, 4, 6, and here we have a positive charge, that means 0. 6 electrons, again 6 electrons, aromatic. This will be very stable. This is not important in order to know if one compound is stable or not. It's also important in the reactivity of this compound. For example, the 1,3-cyclopentadiene, okay, we can do 3 things with this compound. We can remove a proton, a H+, we can remove a hydride, H-, or we can remove a radical, H electron. Okay? If we remove a proton, H+, what we get is a negative charge on the ring, and as we saw before, will become aromatic. That means that it's very stable. That means that this reaction will work very well. When we gain aromaticity in a reaction, this reaction is very favorable. Why? Because the final products are very stable. When we remove a hydrogen radical, what we get? We get a final compound with 7 electrons. It's not with 5 electrons. It's not aromatic. It's not anti-aromatic. It's simple no aromatic. However, when we remove a hydride, what we get is a carbocation. That means that now we have a cyclic ring with 4 electrons, anti-aromatic. That means will be almost impossible, because remember that anti-aromatic is very unstable. That means we have one reaction that is working very well, that is the elimination of a proton, one reaction that is working very bad, that is the elimination of hydride, and one reaction that is more or less in the middle. Okay? And again, when we make a reaction that is gaining aromaticity, this will be very, very favorable, will be very easy to do. In this case, what we can see is that if we have a carbon-hydrogen bond and we want to remove the proton, the acidity of this compound is around 30-something pK. However, in the case of the cyclopentadienyl, because we are forming an aromatic compound at the end, the acidity of this hydrogen, that means the affinity in order to remove this hydrogen as a proton, has a pK of around 15. That means it's very, very, very low if you compare with the 30 that we had before. That means that this process is very favorable. Exactly the same that if we have a cycloheptacryene. Okay? In the case of cycloheptacryene, will be the opposite. If we form a carbocation, this will be very stable because we have 6 electrons, aromatic. That means the elimination of a hydride will be very easy, while the elimination of a proton, that will give us a compound with 8 electrons, then anti-aromatic, will be very difficult. Okay? That means predict if the final compound of a reaction gets aromatic or not will tell us if the reaction is easy or not. Here we have an example. Okay, we have cyclooctatetraene, and the problem 15.7 says that reacts with potassium metal, forming the stable cyclooctatetraene dianion. Okay. Why we suppose that this reaction occurs easily, and what is the geometry that we expect for the final compound? Okay. What we need to do? Well, the final compound is cyclic. All the carbons are sp2 of the ring. All the atoms of the ring are sp2. Okay, and how many electrons we have? We have 2 of this bond, 2 of this double bond, 2 of this double bond, 2 of this double bond, 8, plus 2 electrons extra that we add with the potassium. What we get is 10 electrons. 10 electrons is 4n plus 2, when n is equal to 2, aromatic. That means if we, in this reaction, gain aromaticity, this reaction will be very, very, very easy. And how will be the geometry? Well, the final geometry, we know that all the aromatic compounds are planar. That means that the final compound will be planar. Okay? Then finally we will talk about heterocycles. Basically a heterocycle is the same. It's an aromatic, heteroaromatic. It's a cycle where we substitute one of the carbon atoms, by one heteroatom. In this case, normally, or nitrogen, or oxygen, or sulfur. Okay? And the rule is that these compounds behave quite similar to the carbon rings in terms of aromaticity. Okay, we have pyridine, for example. Pyridine, we substitute a benzene ring with one of the carbon by a nitrogen. Okay, but if we check of the structure of the pyridine, we can see that all the atoms of the rings are hybridized sp2. Okay, and how many electrons we have? 2 of this double bond, 2 of this double bond, 2 of this double bond. 6 electrons will be aromatic. Okay, it's working the same. If someone of you is asking me, and the pair of electrons of the nitrogen? Well, the pair of electrons of the nitrogen must be in a sp2 orbital. Why? Because we are using the pz orbital of the nitrogen in order to form the double bond carbon nitrogen. Okay, that means that the only option that the pair of electrons has is to be in a sp2 orbital. Exactly the same that if we do with pyrimidine. Okay, exactly the same concept. In this case, the pair of electrons that in each nitrogen are in a sp2 orbital. Okay. In the case of 5-member ring, we can have the example of pyrrole. Okay, and here we can do exactly the same. It's a 5-member ring. All the atoms of the 5-member ring are sp2 hybridized. Okay, and how many electrons we have? 2 and 2, 4. And what I said, all the atoms are sp2 hybridized. That means that the nitrogen must be sp2 hybridized. Okay, we follow the same theory than in the cyclopentadienyl. When we have an atom with a pair of electrons, we can choose that the orbital of the pair of electrons are or a sp3 in the case that we have a sp3 hybridization, or a pz if we have a sp2 hybridization. Okay. In this case, if we want to be aromatic, we don't have any other option that the nitrogen will have a hybridization sp2. That means that the pair of electrons must be in the pz orbital. If the pair of electrons are in the pz orbital, we have 2, 2 and 2, 6 electrons aromatic. Okay, and what happens in the case of the imidazole? Well, in the case of imidazole, it's a very interesting case. Why? Because if we check, we have five atoms, we substitute 2 carbons by 2 nitrogens, and what we have is that one of the nitrogens, this one, the hybridization must be sp2 because if it's aromatic must be sp2, and then these pair of electrons of this nitrogen are in the pz orbital. However, here this other nitrogen is by sure sp2 hybridized. Why? Because it has a double bond nitrogen-carbon already. This carbon-nitrogen double bond is formed by the pz orbitals of the carbon and the nitrogen. If this is happening, the pair of electrons of this nitrogen is in a sp2 orbital. Why? Because the pz is already occupied. That means in this case we have 2 electrons here of the 2 double bonds plus 2 electrons of the pz orbital of the nitrogen down, of this nitrogen. Okay? 6 electrons, because the pair of electrons of the other nitrogen are in a sp2 orbital, are not part of the p system. That means this will have 6 electrons, will be aromatic. In this square we can see another examples of different compounds, heterocycle compounds. Please check it at home that all these compounds are aromatics. Okay? Finally, we can do the problem 15.10 where they say that thiamine or vitamin B1 contains a positively charged 5-member nitrogen sulfur heterocycle. Call it thiazolium ring. Explain why the thiazolium ring is aromatic. Well, it's the same than before. The only difference is that now we have a sulfur that has 2 pairs of electrons in the sulfur. If we analyze the sulfur, if we expect that this compound will be aromatic, that this 5-member ring will be aromatic, the sulfur has to have hybridization sp2. That means if the hybridization is sp2, one of the pair of electrons will be in the pz orbital, the other pair of electrons will be in a sp2 orbital. Then we count the electrons. We have 2 of this double bond, 2 of this double bond, plus 2 of the sulfur, 6 electrons. That means aromatic. If we check the nitrogen must be hybridization sp2 because he's forming a double bond with the carbon. That means that if we're forming a double bond with the carbon, the pz orbital of the nitrogen is reacting with the pz orbital of the carbon, forming a p system. Okay? And why is positive the nitrogen? This is for the nature of the nitrogen. Okay? Nitrogen, if we check the periodic table, is from the group number 5. He has 5 electrons in his outer shell. That means when a nitrogen has 4 bonds, in this case has 4 bonds, 1 double and 2 simple, because there are only 4 electrons around the nitrogen will be positive. Don't confuse this positive with 1 electron less. It's nothing related. Okay, it's positive because he had to have 5 electrons in his outer shell and he only has 4. Okay? And that's all. Please, these are the study questions. Okay, you have all the answer of these problems in Blackboard, made by me, and please read the textbook, chapter 15, 1 to 5. Thank you very much, and see you another day.